The gravitational field is an alteration of space around anything that has mass. The gravitational field is a vector field, which means it has a magnitude and a direction at every point in space. Finally, the units of gravitational field are newtons per kilogram. This is the equation for the gravitational field of a point particle. It depends on the gravitational constant, the mass of the point particle, and the distance from the point particle to the position where the gravitational field is measured. The vector r hat is a unit vector. According to standard definitions, this vector points away from the point particle. The negative sign in our equation thus indicates that the direction of the gravitational field is towards the particle. That is, the direction of the gravitational field is in the negative r hat direction. While this formalism is technically correct, it is not necessarily straightforward. Thus, as you will see in later examples, always remember that an object's gravitational field points towards the object. The gravitational field always points toward the point particle and is thus always perpendicular to the equipotential surfaces of the gravitational potential of the point particle. The magnitude of the gravitational field decreases as the distance from the point particle increases. Now let's calculate the gravitational field of this system of two point particles at the position P. Each of the point particles will have a gravitational field at the position P. Each of these gravitational fields points back toward the associated point particle. It is easiest to calculate these gravitational fields by first determining the magnitude of the field. We can then determine the direction. This is likely easier than determining the direction using negative r hat for each particle. The magnitude of the gravitational field of particle A depends upon the distance between particle A and the position P. We can determine this distance using trigonometry. After performing these calculations, we see that the magnitude of the gravitational field of particle A is g times the mass of particle A divided by 2. We can then determine the direction of the gravitational field using similar triangles. Specifically, the triangle for the x-axis and y-axis components of the gravitational field must be the same as the triangle used to determine the distance from particle A to the position P. Thus, the magnitude of each of these components is equal to the magnitude of the gravitational field divided by the square root of 2. Looking back at our picture for the system, we see that the gravitational field for particle A points in the negative x-axis direction, and the gravitational field points in the negative y-axis direction. Thus, the components of the gravitational field of particle A along the x-axis and y-axis are both negative. We can perform a similar calculation for the gravitational field of particle B. In this case, however, the gravitational field points in the positive x-axis direction and the negative y-axis direction. The net gravitational field of the system is the summation of the gravitational fields from each point particle. As expected, if the masses of the point particles are the same, the net gravitational field has a component along the negative y-axis only.